Sometimes we can undo matrix multiplication, and when we can, it's called matrix inversion. So specifically, for some matrices B, there is a matrix called B inverse, which undoes multiplication by B. So specifically, we can right multiply A by B to get AB. Then we can right multiply by B inverse to get AB, B inverse, and these will cancel each other out. That'll end up being just the identity matrix, and we're back to A like we'd never done anything. Similarly, we can left multiply A by B to get BA, and then we'll left multiply by B inverse to get B inverse BA, which is A. So B inverse, the same matrix is going to work as a left inverse and a right inverse. It'll undo multiplication on the left if we use it on the left, and it'll undo multiplication on the right if we use it on the right. So some important examples of invertible matrices. Matrices whose multiplication we can undo are row operation matrices. Let's look at those closely. Now if we want to swap rows I and I plus 1, that's the same as left multiplication by a matrix that looks like the identity matrix, except two of the ones are in the wrong place. So one's all done in the diagonal except for in rows I and I plus 1, where the ones are just off the diagonal. Now this row operation is its own inverse. Because if you do it twice, if you swap rows I and I plus 1 twice, it's like you never did anything. Now another row operation is multiplying row I by some constant k. So this is the same as left multiplication by a matrix that looks like the identity, except in one position we have a K. And zeros everywhere else. And the inverse of this operation is left multiplication by, well, first of all, what we're doing is we're going to multiply rho I by 1 over K. So this will work if K is not 0. And the inverse matrix looks just like this, except where we had a K, now we have 1 over K. So that undoes multiplying a row by K. Now our other row operation is add K times row J to row I. This is multiplication by a matrix that has 1s on the diagonal and a K off the diagonal. So here's row I and here's column J. So we've got a K in row I and column J. Row I becomes row I plus K times column J when we multiply by this. Now the inverse row operation is subtract K times row J from row I. So if we add K copies of row J to row I and then subtract K copies of row J from row I, it's like we didn't do anything. So that's the inverse. And the matrix is just the same, except we'll have a minus sign here. Now row I becomes row I minus K times row J. Alright, those are a couple of nice formulas for inverses of matrices, which are row operations. But what about all the other matrices which are invertible? Not every invertible matrix is a row operation itself. So the question is, how do we compute B inverse given B, or decide that B is not invertible? Like the zero matrix, for example, is not invertible. The answer is we perform row operations on this n by 2n matrix B I. So we put the matrix B we want to invert over here on the left, and then we put the identity next to it. We perform row operations until we obtain the identity on the left and then something on the right. So that is, we're going to be performing Gauss-Jordan elimination. This is going to be the reduced row echelon form matrix corresponding to BI. this matrix will be in row reduced echelon form, because every one here is going to have zeros above it and zeros below it. So let's do an example of this. So let's say we want to invert the matrix 1, -2, -1, 3. So we write down that matrix 1, -2, -1, 3 with the identity matrix next to it. We want to get a 1 here and a 0 below it, and then a 1 there and a 0 above it. So to get a 0 here is pretty easy. We'll just add the first row to the second row. So row 2 becomes row 2 plus row 1. And we have 1, -2, 1, 0, -1 and 1 is 0, 3 minus 2 is 1, 0 and 1 is 1, 1 and 0 is 1. And then, so we have a 1 here like we want. Now we want to get rid of the -2 there, so we'll add 2 copies of row 2 to row 1. Row 1 becomes row 1 plus 2 times row 2. So 1 plus 2 zeros is 1, -2 plus 2 ones is -2 plus 2, which is 0, 1 plus 2 ones is 3, 0 plus 2 ones is 2, and we have 0, 1, 1, 1. So this means that 3, 2, 1, 1 equals 1, -2, -1, 3 inverse. And we can check. So 1, -2, -1, 3 times 3, 2, 1, 1 is 3 minus 2 is 1, 2 minus 2 is 0, -3 plus 3 is 0, -2 plus 3 is 1. And we can check the other product, 3, 2, 1, 1 times 1, -2, -1, 3. And I'll let you check that one at home. You should get the identity matrix also. Now a good question to ask right now is, why would this work? And the answer is that row operations amount to one big fat matrix multiplication. So every time we do one of those row operations, we're multiplying by a matrix on the left. So that means that going from BI to I something is going from BI to, what we're doing is multiplying on the left by P, so PB, PI. Now, P times the identity is just P. Now, if we do this until we get I something, that means that PB is I, and that something is P. If PB is I, then P is this matrix we're looking for, B inverse. And P equals B inverse is right here. It's whatever ends up on the right-hand side. Now, another question we should be asking is, how do we know that this left inverse that we've computed, something we can multiply by on the left to get the identity, is also going to work as a right inverse? And the answer is, well, we know that P is a product of invertible row operations. That is, it's a process that we can undo if we want to. So that means if we can undo left multiplication by P, that means it has an inverse. Now let's left multiply both sides of the equation PB equals I. By this inverse, P inverse. This gives us P inverse PB equals P inverse. P inverse P is just the identity. P inverse is the matrix that undoes left multiplication by P. So that is that P inverse is B. If P inverse is B, that means we can multiply P on the left by B to get the identity. So that means that BP equals I. But we said that P was B inverse. So that means that B inverse equals I. So B inverse works not only as a left identity, not only as a left inverse for B, but also as a right inverse. And one more remark. So some matrices are not invertible, and we're going to recognize the matrices that are not invertible by trying to perform row operations on BI and not being able to get I on the left-hand side. So if we can't use row operations to go from BI to I something, then B is not invertible. The end.